we're going to have a bit of a detour from doing the maths papers to doing the Level 1 Physics paper, Demonstrate Physical Systems of Energy Concepts, which was on Thursday. I'm recording this on the following Sunday, simply because I've had a lot of requests for people to do this one. They had some trouble with some of the questions and they wanted to see how I would do it. So this is the first time seeing this exam paper. All I'm going to do is use the Casio FX calculator and also the formula sheet that they give you. So first up we have the classic question of lifting something vertically a distance. And we're told that we're lifting a paint pot, which is 40 kilograms, so you should be sort of looking at it and you're thinking, okay, so what are our variables we've got? So we've got our M is going to be 40, it's already in kilograms, so we don't need to put the units next to that. The power in the motor here is given as 250 watts, so I guess we're going to presume that it's going to not need to speed up or do anything, and as soon as we turn it on, it's going to be 250 watts throughout the whole thing. That's often not the case. We lift a 40 kilogram paint pot up the side of a 20 meter long drop. Okay, so our change in height is going to be equal to 20 meters. So it's already in SI units. And the time it takes to lift the pot is 35 seconds. So T is 35, seconds is the SI unit. Describe the energy changes as the motor lifts the paint pot up the side of the building. Well, there's a couple of things that are happening here. So we're going to presume as well, by the looks of it, a very light rope. Okay. So it tells us that there is a very, very light rope. So we're sort of saying that the mass of the rope here is negligible. And it looks like it's on some sort of winding, which is going to complicate things as well. In reality, of course, nothing which is 20 meters long is going to have no mass, but for our sake, we're going to say that it does. All right, describe the energy changes as the motor lifts the paint pot up the building. So the first thing that's going to happen is the paint pot itself, as it goes up, so it's going to gain gravitational potential energy as it goes up. Okay, as it's moving, it's also going to have some kinetic energy. And the kinetic energy, we can work it out. So we're going to presume that it's a constant velocity that's moving up. Is going to be half times the mass, which is 40, times the distance, the 20 meters over 35 seconds squared. So it's going to have that while it's moving. That's the paint pan, the paint pot, and the potential energy at the top is going to be mg, change in height. So that's going to be 40 times 10, which is given, times 20. So that's going to be 8,000 joules at the top. Now the motor here, so this is going to be converting electric energy into mechanical energy. Okay, and it's going to do that at a rate of 250 watts. So 250 watts means 250 joules per second. So this motor is the total amount of energy that it's going to convert from electrical energy is going to be 35 seconds times 250 watts. So it's going to be some number. Okay, it's never going to be perfect. Of course, we're going to get entropy. So this thing is probably going to give off some sound energy. It's going to come off it, and it's also going to give off some heat as well. Remember, entropy means we can never have a perfect process. It's always going to be imperfect. We're always going to lose some of the useful energy. That's about it, really. So we're converting electrical energy into mechanical energy, into kinetic energy, into gravitational potential energy at the top. And that's more or less all there is. So I kind of anticipated this question. Compare the amount of energy provided by the motor with the gain in gravitational potential energy. So the energy that's used up by the motor, well, we know that that's going to be power times time. It's work, the amount of work. And remember, you can think of work as the energy expended to do something. So here we've got the power, which is what was it? It was 250 watts. 250 watts times 35 seconds. It's going to be a number. So, there. 250 times 35 is 8,750 joules. So the work energy equivalent formula comes to our rescue here. Okay, the change in potential energy is, of course, mg change in height, and this is going to be the mass is 40 kg. We're going to say that gravity is 10 newtons per kilogram, and the change in height is the 20 meters. It's going to be positive, so it's going to gain potential energy, and that's what 40 times 10 times 20 is 8,000 joules. So what is the difference here? Well, the difference here is entropy. So we are losing some of the energy that goes into this motor in the form of heat and sound, I guess, and through friction sometimes, I guess, as this pot moves through the air. But you're never going to get a perfect yield from the energy that you put in. The amount of energy that you get out is always going to be a little bit less than you started, and it's 750 joules worth of energy over 35 seconds. That's not too bad. That's actually pretty efficient for electric motors. So now we're asked to picture the rope breaking. You get when you get a massless rope. Discuss the energy transfer from the paint pot from the top of the building to when it is halfway down. I want a diagram, so here's the pot, and it's going to fall in a distance of 10 meters when it's halfway down. Okay, well, it's going to convert half of the gravitational potential energy into kinetic energy. So some amount of kinetic energy. How much is that? Well, let's work it out. So the change in potential energy is going to be mg change in height. Well, the change in height is going to be just 10. So it's as if it's fallen 10 10 meters, and then it keeps going, but we only care about it as if it was frozen at this point in time. So it's 40 kilograms times gravity, we're saying it's 10, and we're saying here that the change in height is 10, so 40 times 10 times 10 is 4,000 joules lost from potential energy into kinetic energy. We started with, what did we start with? We started with, at the top was 8,000 joules. So 4,000 of those joules have been converted. What else could you say? Let's work out what the velocity of this thing is going to be. So the kinetic energy is going to be half mv squared. We know that's equal to 4,000. So half times 40 times the velocity squared equals 4,000. So 20 times v squared equals 4,000. So v squared is going to be equal to 400 divided by 20. We lose 0. This is going to be a 2. So this is going to be 200. So the velocity, let's sort of go here, velocity is going to be the square root of 200. So square root of 200 is 14.14 meters per second. Presuming that all of the gravitational potential energy has been converted into kinetic energy, because we know from our studies of energy that you're never going to get a perfect transformation. All of the energy you put in is not always going to equal the amount of useful energy that you get. You can't destroy energy, but you're going to lose some of that useful energy anyway. All right, the next question asks us to consider the pot, if it falls the 20 meters, so it's going to hurtle down this copyrighted grey box here, 20 meters, and we worked out that the potential energy at the top is going to equal to the kinetic energy at the bottom, plus a little bit of heat, plus a bit of sound, mainly through friction. Okay, friction is a force that does work to slow it down, and it's going to convert some of that into heat. I mean, a tiny, tiny amount. So when we work out the velocity using this relationship here, we can work out the maximum velocity, and it can't exceed that velocity unless there's some downward draft pushing it down, and there isn't in this case. So we already worked out at the top the gravitational potential energy at the top was 8,000 joules, and we're going to set that to the kinetic energy at the bottom, which is half times mv squared. We already worked it out halfway, so we know that this velocity squared must be the square root of 400. Don't believe me, just sort of work it out. So half times 40 is 20. 20 divided by 8,000 is 400. So the velocity squared is 400, which means that the velocity when it hits the bottom is 20 meters per second maximum. It's actually probably going to be something like 19.8 meters per second, something like that. We're going to lose a little bit to heat. a tiny, tiny amount, but it's not going to be perfect. Question 2, keeping warm. Lower is in the lounge and feeling cold. She connects convection heater to the power supply and switches it on. She places the heater in the room and notices the temperature of the air begin to rise. The air itself will begin to rise as well. Compare the concepts of temperature and heat energy. So heat energy is the kinetic and potential energy of all particles in the room. Okay? That's what heat energy is. Temperature, and my neighbour's dog is barking. Temperature is the average. It's the average kinetic energy measured. Right? So they're related, sure, they're related, but they're not the same thing. So you couldn't really say that temperature is a sort of a measurement of the average kinetic energy. Heat is just all of the heat that's in that system, and our system is going to be this room here. So this is our system, and it's better to say everything that can be heated. So immediately it would be the air, but also note that everything is going to itself warm up, so that's going to radiate, convect, and conduct heat as well. So measuring the heat is a lot harder than measuring temperature, but temperature is a good way of measuring the amount of kinetic energy that's in the room. And remember, kinetic energy is going to be the sum of all of the half mass times the velocity of the particle squared. So as there's more kinetic energy in there, we're not going to be able to change the mass, but the velocity of those particles will go up. And that's what we measure when we measure temperature. All right, now we're told to notice the maximum power rating is 2,000 watts. So that's the amount of energy per second that the heater can use. The voltage supply in her house is 240 volts. She sets the dial at 50% maximum, so I guess we presume it's going to be half of the power. Okay, calculate the current in the circuit. So we want current, and current is in amps. Now I've got a wee little technical gripe with this question. 240 volts is the average. It's the can't remember the exact word, but it's kind of like the average voltage, and you would get an average current, because if you look closely at this tag, let's actually see if we can increase the size of this. If you look here, it tells us something really, really important. So here's something really, really important. So it's 240 volts, 2,000 watts, but there's something else here, 50 hertz. And that means that it's not a direct current system, it's an alternating current, which means it's a sinusoidal power supply, so it's going to go up and go down. Sometimes there will be more than 240 volts and the accompanying current. Sometimes there'll be a little bit less. So we're going to kind of make out as if this is a DC power supply. And it's okay because you haven't done alternating currents in class. You don't get them until I think the end of year 12 and definitely in year 13 physics. But we're just going to go with that for now. 240 volts, 2000 watts. All right. The 2000 watts is the power, and we know from our formula that power is the current times the voltage. If we set the voltage at 240, which is fixed, and we set the watts, the power to 2000 watts, and it's going to be half that, isn't it? So it's half of that. It's going to be equal to the current that's going through this heater times 240 volts. So the current is going to be 1000 divided by 240, which is going to be some number. It's going to be a little bit more than 4. So 1000 divided by 240. So 4.1666666. So 4.2 amps. 4.2 amps. That's current. But again, it's an alternating current, but we'll sort of say that that's the average amount of current that's going through there. All right, the next one was the one that tripped quite a few students talking to them. And it was this one. So they say that the current, she turns the dial on the heater, which increases the current in the heater, which is kind of against what was in the last question, I guess, but we'll go with that. Okay, so if the power to a maximum of 2000 watts is the current times the voltage, and the voltage is 240, well, we need to work out the energy, the thermal energy that's going to be released, and it's going to be this one here. It's not PAT, so it's power times the change in time. So if we keep the change in voltage as 0, so the voltage is set at 240, and that was the bit that tripped quite a few students up. If the current goes up, then the power must also go up. It's just a mathematical relationship. If this is kept constant, if this goes up, then this must go up, because there are no other variables, and nature hates things not to equal. If the power goes up and the time is going to be kept constant, it must mean as well that the amount of energy that's being used up must also increase as well. Okay, so I guess we could say, so as current goes up, we could say that the power must go up, and as the power goes up, the energy being released, converted, must also increase. And that's going to increase the kinetic energy in the room, which is going to increase the temperature and the thermal energy in the room. So that's how you would answer that question. I wouldn't get hung up on the other formulas that deal specifically with the thermal energy, which is the MC change in temperature, or the thermal with the latent ML. So I wouldn't use those. I would use these two formulae. You're going to get into a lot of trouble if you use these, because we're not really talking in change in temperature. We're talking about change in time. So if the time is kept the same, I guess we could say that the thermal energy, must also increase. because the heat capacity of the air and the mass of the air is going to be constant, I guess. I guess if you're going to include those, but really you would just include those two formula that I've given there. There isn't a good explanation. I might do a different one if you really want one. So here we're going to get a kind of a little Cournot cycle. The hot air is going to leave this, so it's going to radiate in all directions. And then the kinetic energy of the particles means that they want to make up more space. There's more inelastic collisions, which means that the heat is going to want to take up more space, which means it's going to rise. And when it gets to the top, it's going to cool down. And when it cools down, it's going to fall and it's going to be hit. So there's going to be a sort of a cycle here. You could say that the kinetic energy at the bottom of these things is here. So the kinetic energy here is less than the hot kinetic energy there. But that's the basic shape that you'd want to put. You'd want to put it. Basically, heat air rises because it wants to expand upwards and outwards, and the only place that can go is up. It's going to, and the fact that it has more energy, it can overcome gravity by rising, and cold energy, because it has less kinetic energy, can't overcome gravity, and therefore it falls. So I've got the hiccups. So this is the one that really caused students a lot of trouble. I had a lot of messages about this one. It's not the first couple that were the problem. It was the third and fourth bits. So we're told that Cecilia, is that how you spell Cecilia? Is that a funny spelling? Okay. She wants to measure the specific heat capacity of water. So this is an experiment that's been done tens of thousands of times, everywhere from high school science classes to university to multi-million-dollar tests. It's really, really important to know the specific heat capacity of water. It's a really, really important thing to know if you want to do engineering. So the specific heat capacity of a substance is the amount of energy, amount of thermal energy required to increase or decrease one kg of that substance by 1 degrees Celsius. And next year you'll be 1 degree Kelvin next year. That's what it is. So we've got here we've got half a kilogram of water, so half a litre of water. How much energy needs to be put into that? Oops, should be red. How much energy needs to be put into that in order to raise the temperature by 1 degree? That's what the specific heat capacity is by definition. All right. Next one. Show that the electrical energy used by the hot plate over 10 minutes, and they give you how many seconds that is 72,000 joules, so 72 kilojoules. Well, okay. We don't really care about the water, we only care about the hot plate. So we're given that the hot plate is 24 volts, and we're told that it has a current of 5 amps. So that's up here. All right, so that means that the power that it puts out is, of course, IV, which is going to be 24 times 5. So whatever that is, so 24 times 5 is 120 watts. But what is a watt? What is a watt? A watt is the amount of energy that it uses per second. So to work out the amount of work that it's going to do, the amount of energy it's going to expend, it's going to be power. So the work that's done is going to be the power times the time. So it's going to be 120 watts times 600 seconds. And my bet is that if we multiply these out, it's going to be 72,000. So we've got 120 times 600, 72,000. So 72,000 is in work and energy, so it's going to be in joules. That's how you can answer that. It's just really an algebra question, knowing what the letters mean. Okay, now we get to the bit I think that stumped a lot of students. So we're told that Celia graphs the increase in water temperature over time and obtains the following result. So the time that's taken is 600 seconds, so T is 600. And we're told that the mass is 0.5 kilograms of water, and that 72,000 joules of energy was used. So we're presuming that it's all going into the water. So we would then come along and say, okay, we've got our equation says this: NC, change in temperature. All right, so the time is kind of irrelevant. It's kind of the change in temperature, not the change in time now. Remember, big T is temperature, little t is time. And we're wanting to work this out. No, we're wanting to work that out. You know what the mass is. So 72,000 is going to equal 0.5 kilograms times C. Now what's the change in temperature? Well, we start there at 20 and we go to 60. So the change in temperature is 40 degrees. And again, we don't care if it's going up or down. It's just the change that we care about. All right. Now it's just an algebra problem, isn't it? So let's take it off to one side here. So 0.5 times 60 is 20 times C. So therefore C must be equal to 72,000 divided by 20. All right, and let's grab our calculator and work it out. So 72,000 divided by 20 equals 3,600. So 3,600, and it's going to be in, what is it going to be in? It's going to be in joules per degrees Celsius -1. Okay, now there is a bit of a problem here. The heat capacity of water is generally, and I just remember this from school, it's kind of drummed into us at school, the heat capacity of water is given almost universally as 4,200. Excuse me. Where does that 600 joules per degree go to? And we have a problem because not only is it not what we would expect, it's actually on the wrong side of what we would expect. So what I mean by that is that we would expect the number that we get to be greater than 4,200 because we're going to lose some energy here in the hot plate. We're going to lose it to the atmosphere. There's going to be entropy there. We're going to lose a bit of efficiency maybe in the plate itself. So one of two things must have happened. One of three things must have happened. The first thing is that Cecilia is correct. Okay? And the specific heat capacity of water really is 3,600. If that's the case, then Cecilia can expect a Nobel Prize in the post next week. It is very, very, very unlikely that her experiment disproves 200 years of observations. Maybe Cecilia has special magic water that doesn't require as much energy to heat up. If that's the case, then she's going to be a billionaire. If she can find this magic water, she's going to be fantastically wealthy. Okay. The second possibility is that there is a measurement error. Because if anything, we would expect it to be 4,300, like the other side of 4,200. So, in other words, the thermometer is wrong or something is wrong. The other possibility is that there is an experimental error. And this is the most likely cause. It looks like she's got it set up pretty well. I mean, the thermometer is, you'd be really worried if the thermometer was touching the bottom element, because then it'll be just taking heat from the element, not from the water. It's kind of done up good and proper there, so that's not too bad. Okay, what I think is probably most likely have happened is that she needs a stirrer. And what's going to happen is that when she has this water, the water is going to, there's going to be convection currents. Okay? And there are going to be hot spots in the water, especially near the bottom, where the bottom of the thermometer is. What she needs is a stirrer. So usually there's kind of like a little magnet that you can stick into these things, and it sort of rides on an electromagnetic force field and spins. And it spins around inside there, and it mixes the water so there is a nice uniform temperature. And this is probably what's happened. Okay, and I'll kind of answer it here. So the expected value is 4,200. The fact that she has less than that, I'm going to call it actual. She may have made a mistake. The actual observed is 3,600. Now that's a lot. Right? That's what? 600 divided by that's a 15% error. So there's a 15% error. There's probably a problem here. Science loves when you can find something, when you can disprove something, but you're going to need a lot better evidence than that to disprove the specific heat capacity of water. It is a very, very established physical constant, well, physical measurement, and the chances that some person in a New Zealand Year 11 science classroom has disproved that is unlikely. It's possible, but it's very, very, very unlikely. Okay, what can she do? Well, I've just sort of gone through, so she could check the apparatus, check the measuring equipment, and make sure that it's calibrated properly, and have a stirrer, I'd say. Whenever you're dealing with something with liquids, especially change in temperature in a liquid, you really always want a stirrer. You want a nice uniform change. And you probably want insulation and stuff like that. So this question really stumped quite a few students. That is how I would answer it. So hopefully that's some help for you. I may revisit this at a later stage, but that's how I would answer it. Okay. Have a good week.